In this video, we're looking at Unit 7B. Oops, sorry about that. And combining probabilities. We're going to start off with a little story here of a French con man and how he incorrectly calculated probabilities, and this eventually led to him losing money, and so he turned to mathematicians who started to look at this idea of probability a little bit closer and began coming up with some ideas and some theories on probability. So it was 1654, French conman known as the, and I can't say that, Chevalier de Mer. I don't speak French, but he bet other gamblers even money that he could roll at least 1 6 in 4 rolls of a standard 6-sided dice. So he made a profit on this bet, although he had calculated his chance of winning incorrectly. So when you look at the probability of rolling a 6 in 1 roll, that probability is 1/6. So the Chevalier falsely reasoned that his chances would be 4 times greater, or 4 times as great with 4 rolls. So if he rolled 4 times, he'd have a 4 out of 6 chance, which is about 0.67 or 67% chance of rolling at least 1 6 in 4 rolls. So it actually shows that in 4 rolls it's only 52%. And we'll go over that here in a moment. A chance of getting at least 1 6 in 4 rolls. Nevertheless, because the probability is 52%, that means that 52% of the time he's winning and only losing 48% of the time. So over the long run, this individual profited. Now, as gamblers caught on to his con game, they weren't willing to pay any longer. So this guy proposed a new game, which he would roll 2 dice, and he would bet that he could throw a double 6 within 24 rolls. So he knew that only in a single roll of 2 dice, the probability of rolling double 6 is 1 out of 36, because there are 36 outcomes when you have 2 dice. And that's, if you look at 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 2 2, and so forth, there are 36 different possible outcomes. So there's a 1 in 36 chance that you'll get 2 6s. He then used his faulty reasoning to guess that if he rolled the pair dice 24 times, his odds of rolling at least 1 6 or double 6 would be 24 out of 36. So if you just took the 1 out of 36 times it by 24, he would again get 0.67. Now he was shocked because he began losing money. So in order to understand his losses, he turned to one mathematician, Pascal, who in turn began a correspondence about probability with Pierre de Fermat, and both of them quickly recognized the error in his reasoning and developed some methods for combining probabilities. So those are what we're going to study here, but it's kind of an interesting story as to how some of these things came about. And so one of the things they discovered was what's called this AND probability when you're dealing with independent events. So 2 events are independent if the occurrence of one event does not affect the probability of the other event. Such things as rolling 2 dice. It's one doesn't affect the other. If you flip a coin once and then you flip a coin again, the first outcome doesn't affect the second outcome. So when we look at 2 independent events, so events A and B with probabilities P of A and P of E, the AND probability that both A and B occur, so this is like what's the probability of getting a heads and a heads if you're flipping a coin. If they're independent, the probability of A and B is just the probability of A times the probability of B. And this principle can be extended to any number of independent events. So if you have A, B, and C are all independent, then it's probability of A times probability of B times probability of C. So, with that in mind, we're going to go back and we're going to consider the first bet in which this guy guessed the probability of rolling at least 1 6 in 4 rolls would be 4 times the original probability of 1 6, or 4 times 1 6, which is 4 6. So if we extend his logic, let's see what we would find for the probability of rolling at least 1 6 in 5 rolls. So again, you would take 1 6 and multiply it by 5. So in 5 rolls, he would assume that there is a 5/6 chance of rolling at least 1 6 in 5 rolls. And then if you extend that further, in 6 rolls, then you would take 1 6 and times it by 6, which is 1, which that means it's guaranteed, the probability of 1 is guaranteed to happen, that if you roll a single die 6 times, then guaranteed you'll see at least 1 6. And I think probably anyone here can quickly go grab a die, roll it 6 times, and find a certain number of, or a little window of 6 rolls where you did not get a 6 within those 6 rolls. So his fundamental theory of just taking the probability and times it by the number of times you do that, or you want that outcome, it is very false, and it kind of falls apart right there. So that's where we look more at this idea right here, and we'll look at how we actually find that probability more towards the end here. Now, another thing that we need to talk about in and probabilities is when we get what are called dependent events. So 2 events are dependent if the occurrence of one event affects the probability of the other. So when we're talking about the and probability of dependent events, then the probability of one thing happening and the other thing happening is the probability of the first times the probability of the second, given that the first has happened. We'll look at some of these examples here, but one example is if you have like a bag of marbles and you've got different colors of marbles and you pull one out, there's a certain probability, say you pull out a red. There's a certain probability that you pull out a red, but if you don't put the marble back, now you've changed that size or the number of marbles in the bag, so the probability of drawing a red or a different color, it changes because the number of marbles in the bag has changed. So that's what this probability of B given A means, is that one affects the other. And given that the first has happened, what's the probability that B will happen? And we'll look at that. Again, it can be extended, and this can get a little bit messy. We won't get too messy in this, but it can be extended to 3 and beyond. Okay, let's look at some examples here. We want to look at some and probabilities. So determine whether the events described are independent or dependent. Then find the and probabilities of an event. And when you see and, think multiplication. That's one thing I wanted to point out. I forgot about that. When you see and, you want to think multiply and probability. So multiply when you see and. So what's the probability of getting 5 heads when you toss 5 fair coins simultaneously? Okay, these events are definitely independent. The flip of one coin does not affect the flip of the other. So the probability of the first being a heads is 1/2. You have 1 out of 2 chance. For the second coin, it's 1/2. For the third coin, it's 1/2. For the fourth coin, it's 1/2. For the fifth coin, it's 1/2. So you get 1/2 times 1/2 times 1/2 times 1/2 times 1/2, or 1/2 to the 5th power, which is 1 out of 32. So you have a 1 in 32 chance, or probability, that you will roll or flip 5 coins and get 5 heads. Okay, the next one, rolling a fair die, and that's a key idea there. Make sure it's not weighted. But a fair die 3 times and getting in order 1, 2, and 3. So again, one roll is not going to affect the other, so these are definitely independent. And on the first one, the probability of getting a 1 is 1 in 6, because there's 6 sides. 1 only occurs on one side. The probability of getting a 2 is also 1 in 6, and the probability of getting a 3 is also 1 in 6. So you get 1 in 6 cubed, or 1 out of 216. That's the likelihood of rolling a 1, then a 2, then a 3 when you are rolling your dice. Okay, the next one, drawing 3 aces in a row from a standard deck of cards when the drawn card is returned or replaced to the deck each time. So you draw it, you look at it, and then you put it back in the deck. So our probability here, again, we want 3 aces. Well, how many aces are in there? There are 4 aces out of 52 cards. So you get 4 out of 52 for the first one, then you replace it. So it's 4 out of 52 for the second, and 4 out of 52 for the third. Because again, we're replacing that ace in there. So when you multiply all of those together, you get, it reduces down to 1 out of 2,197. Okay, and that's, again, that's when it's returned or with replacement. Now, what happens if we say that without replacement? You take the card out, you look at it, and then you don't put it back in the deck. Okay, this becomes dependent. So the first one was independent. I forgot to write that. So the first one's independent. The second one is dependent with when you don't replace, because the probability of getting the ace on the first one is 52, 4 out of 52. But then the probability on the second, assuming you got an ace on the first one, there's only 3 aces left and there's 51 cards remaining in the stack. And then on the third, you've drawn 2 of your aces, so you're down to 2 aces, and you're down 2 cards, so 2 out of 50. So you have a 1 out of 5,525 chance. So you can see how the dependency there bumps up that likelihood, or scales it down quite a bit when they're dependent, because again, these two are dependent upon what happened before. So that's a look at one problem that can be dependent or independent. Okay, now let's look at, what's the probability of selecting an all-male 5-person jury from a pool of 10 men and 10 women. So we have 20 people, and we want to know the probability that every seat is filled by a male. So all 5 people are male. So the first one, there are 10 males out of 20. So the likelihood on the first person to fill the first seat, you have 10 out of 20 chance. But then this is, again, I should have wrote this down, but this is dependent because the second one depends on how the outcome of the first one went. So then if you draw a male in the first one, you're down to 9 males out of 19 people left to be selected from. And then down to 8 males for the next seat out of 18. And then you're down to 7 out of 17. And then lastly, there are 6 males to choose from out of 16 people. So if you reduce those fractions, multiply all the way out on this, you'll get 21 out of 1,292. And that's your probability there. So again, dependent on that one, because once you select a person, they come out of the group. And so that's why we see this decrease in numbers here and decrease in numbers here, because that's assuming we pick a male and then they're out of the group, and then we're looking at the new set of group, and so there's a lesser number to choose from. So that's a look at AND probabilities, and in the next video, part 2, we're going to be looking at OR probabilities.